Okay. So let me start by recalling few facts. I assume that T is greater than 0 and H bar is a constant greater than 0. And I consider two functions f and u star, which is defined from the torus cross the set of probability measure on the torus into R. So for the moment, I don't make any assumption on f and u star, but soon I will be more specific. And the mean field game equation is find W from 0t cross the torus to R, and sigma from 0t to the set of probability measure on the torus, such that the derivative of sigma with respect to time plus the divergence of sigma gradient of W equal to h bar over 2 Laplacian of W of sigma dt of W plus 1/2 gradient Q of W squared plus F of Q sigma T equal to h bar over 2 Laplacian Q of W, with sigma at time t is mu, and u W at time 0q is u star of q sigma of 0. So this thing in the box, yesterday I wrote it wrongly. I think yesterday I forgot to add the sigma. So you need to make this correction. And so in the data, I am going to assume that mu in the set of probability measure is given.
You consider U star as which depends on sigma 0. This over the time, usually, the initial condition of W. So U star, it depends on Q and sigma of 0. And
yes.
This the overdetermined, no? Because so usually you put the initial condition for W and the terminal condition for sigma.
Yes. So this is not an initial value problem. In an initial value problem, you will put a condition on sigma 0, and you put a condition on W 0. But that initial value problem, it is unlikely that you find existence of solution for large time. So here, this is a problem where you have a terminal value problem for sigma,
Yes,
an initial value problem for W.
Yeah, that I know, but I'm just thinking, I think you need some compatibility condition to okay, I will ask you first.
Okay. So here is when you want to study geometric property of the torus, you can just study geometric property of RD, and then quotient RD by Z to the D. Similarly, if you want to study geometric property of the set of probability measured on the torus, you can just study property of the set of probability measured on RD and then quotient them by a relation. So I am going to study this space instead of studying that space, although this is the space we need. But all the results you get here, you can translate them there because these are special, this is a special subset of that. So I want to impose a condition on F and U star. Let me start by the notation. P2 of RD. This is the set of mu Borel probability on RD such that the second moment of nu is finite. I would like to say that F is of class C2 and U star is of class C2. But before I can do that, I need to endow this with a differential structure. If I endow this with a differential structure with a tangent space, cotangent space, then I'll be able to define a function which is of class CK. So let me start by introducing omega is 0, 1 to the D. H, the Hilbert space, is L2 of omega. So this 2 has to do with that 2, RD. This is the Hilbert space. And on that space, xy, the inner product, the L2 inner product between xy is the integral over omega, x of omega, y of omega, d omega. And I am going to denote by LD of omega. This is the Lebesgue measure. On omega. Now, assume I have two sets, E and F. And I have a map, X, which is from E to F. And assume I have a measure, nu, measure on E. I can push forward this measure to define a measure on F by the following. So given E, a set E with a measure mu, given a set F with a map X from E to F, we can define a measure on F, which will be the push forward of nu by X. And that will be defined the following way. it will be defined as a new T push forward new. If I apply to a set B, this is by definition new of S inverse of B. So this is true for every B subset of F. So example, assume that E is my set omega, and the nu is the Lebesgue measure on omega, and the X is from omega into RB. The push forward of LD of omega, this is what we call the law of X. So the law of S is a measure defined by LD omega of X minus 1 of B for every B subset of RD. So what I want to do, I want to introduce a differential structure. I want to define a metric on the set of probability measure, but I am going to use an approach which is different from what we have done a lot. I am going to use an approach which is going to view the set of probability measure as a subspace of the Hilbert space. And since we have a differential, we understand well what is the differential on the Hilbert space. It will be easier to conclude what is the differential structure of the set of probability measure. And recently, I have proven with Todorescu that this definition coincides with the definition which has been used for the last 10 years. Except that with the new approach, you don't need to rely a lot on measure theory. So let me define an equivalence relation. On H. Let X, Y in H. We say that S is equivalent to Y. And we write X equivalent to Y if the law of X equal to the law of Y. So in other words, if you push forward the Lebesgue measure by X, you get the same thing as if you push forward the Lebesgue measure by Y. So you look at the application which goes from the Hilbert space to the set of probability measure on RD. Right? Because if you give me an element of H, the law is a probability measure on RD. I make the following statement. Fact. First, if X is in H, then the law of X has finite second moment. So not only it is a probability measure, but it is a probability measure with finite second moment. Second, the law from H to the set of probability measure of finite second moment is surjective. So let me prove our idea of proof. The integral over RD of S squared mu dx equal to the L2 norm of S squared if mu is the law of X. Therefore, this is finite if and only if that is finite. So I am going to come back to this, how I get to this identity. Second, the mass transport, the optimal mass transport theory. And show that if mu is in a set of probability measure of bounded second moment, then there exists phi convex such that the law of the gradient of phi is mu. So now let me come back to this statement. So remark. Assume that X push forward the Lebesgue measure to mu. Assume. And I am going to write what this means. This means mu of B is the Lebesgue measure of x minus 1 of B. For every B, subset of RD, Borel. Now let me write that equivalently. The left-hand side is the integral over RD of the characteristic function of B, d mu. The left-hand side is the integral over RD, the characteristic function of B, composition X, d mu. And this holds for every B in RD, Borel. If you take the set linear combination of characteristic function, you get any continuous function. So you can approximate any continuous function by a sequence of combination of characteristic function once my measure is fixed. So this is equivalent. This is equivalent to the integral over Rd of f d mu is the integral over Rd f composition x d mu for every f which is a continuous function on Rd. I can take f non-negative, or I can take, all I need the left-hand side to make sense. I can take f non-negative. I can take f arbitrary but bounded. I can take f in L1, provided that this makes sense. Now, for example, take f of x equal to the norm of x squared. The integral over Rd of s squared mu dx is the integral over Rd of f d mu. This is the integral over omega of f composition x omega d omega. This is the integral over omega of x of omega square d omega. And that is what I wrote there. So next, I want to argue that the set of probability measure is a quotient space. But before this argument, let us develop our intuition, why this is possibly true. You can approximate any probability measure by average of Dirac masses. Therefore, if you can understand the set of average of Dirac masses, then you understand the set of probability measure. So let En be the set of Dirac average of Dirac masses. This set, you can view it. I take omega to be 0, 1 to the d, and I cut it into subset of same measure. So call this S1, S2, all the way up to Sn. Now, I am going to take a sum of Sn, Si, I from 1 to n, characteristic function of Si, Fn, such that S1, Sn is in Rd. This is a subset of my Hilbert space, and there is a one-to-one bijection between this and that, up to the fact that I allow to permute the Si. So I can also identify this set as RD cross RD, but I will have too many elements. If I quotient that by the set of permutation, I see a one-to-one bijection between this set and that set. And I will think of the set of permutation as a particular case of a set of measure preserving map. So if you take up this decomposition of my set 0, 1 to the D, you can construct a measure preserving map which will send a set Si to a set S sigma I for each permutation. And so to each permutation, sigma, I associate a permutation of the set Si. So it tells me that this set, taking into account permutation, that set and this set are the same. And then I want to write the infinite dimensional version of what I said, and you need to prove that the infinite dimensional version is true. Now, here is a result from probability measure, which is going to convince you. All the results. So let S be the set of S of G from 0, 1 to the power D into 0, 1 to the power D, which are Borel, bijective. So bijective means I remove up to a set of 0 measures. They are bijective. And push the Lebesgue measure forward to the Lebesgue measure. So S is going to push the Lebesgue measure. In other words, the law of X of G is LD of omega. So this is the set of measure preserving map. There is a result of probability measure which says let X and Y be in H. Then the law of X equal to the law of Y if and only if there exists a sequence Gn in S such that when you compute the norm of X minus Y composition Gn, the limit when n goes to infinity is 0. So if G was independent of n, I would have written that the set of probability measure on RD is the Hilbert space quotiented by S. But the result is something more subtle than that. In fact, if you compute the closure, the L2 closure of this set, you get the set of measure preserving mapping where you lose the bijective property. You can characterize completely the closure of that set. And so hoping for such an equality is not possible. So once you have this, then this tells you that you are in a good direction to show that the set of the Hilbert space H quotiented by the equivalence relation is the set of probability measure. So let me state that as a theorem. Before the theorem, I am going to do the following. Definition. let mu naught and mu1 be probability measure on RD of second moment. Now, minimize over x naught and S1 in H. S naught minus S1, the L2 norm, over the set S naught S1 such that the law of S naught is mu naught and the law of X1 is mu1. And give a name to this. I'll call it W2 of mu naught mu1. So, theorem. First, W2 is a metric. On P2 of RD, called the Wasserstein metric. Second, if you define the law on the quotient space H into P2 of RD is an isomorphism. So the first statement is true for any equivalence relation. If you take a space and you quotient that by an equivalence relation, and you define a metric, a quotient metric, you define a quotient function, this function will be a metric under some mild condition. And so this first statement is immediate. The second is a tautology, right? Because once we know that this is the Wasserstein distance, then it becomes a tautology. Now, reminder. H is an infinite dimensional manifold. If X naught is in H, then the tangent space at S naught is H itself. The cotangent space at S naught is H itself. So this is the tangent space and the cotangent. Okay. So I take a point in the manifold and I ask myself what is a tangent vector? Zeta, a tangent vector, in H mean zeta is from omega into RD, and the norm of zeta square is less than infinity. So once I realize that a tangent vector at a point is a vector field, then if I go to the quotient space, there will be no surprise that a tangent vector at a measure must be a vector field. Consider the differential structure on the set of probability measured on RD is inherited from that on H. So let me give a meaning to what I am saying. So here is what I am saying. Let us look at a function U from the set of probability measure of finite second moment into R. And I am going to define a lift. This function is defined on the quotient space. Set U bar from in H, let U by H be defined U bar of X is U of the law of X. Here is my statement. This is due to myself and to Dorescu. So we make a statement more subtle than that, but not to enter into technical detail. I am going to make a more general statement. So if you want to do a fine study, you should state this theorem for super differential and subdifferential. You should state a theorem saying that being in a subdifferential of this is equivalent to being the subdifferential of that. Being a super differential of this is equivalent to being super differential. And so that is the statement we had. However, you have to be careful about what you call subdifferential here. This is not a flat space. So I will refer to a gradient. If I take an element of a subdifferential, I'm going to take the element of minimal norm, and I'm going to call that gradient. So when I talk about a differential, I'm referring to element of minimal norm. And the statement is the following. U is differentiable at mu if and only if U bar is differentiable at X, where the law of X equal to mu. In that case, if you take the L2 gradient of U bar at X naught, it is the gradient of U at mu composition S naught. So this look like this may look at first like a strange theorem, because if the structure on the quotient space is inherited from the strut on H, this is trivial. But what I am hiding here is for several years, we have a concept of differential defined by Ambrosio, Gigli, and Savary. And what this theorem is saying is the concept of sub-differential defined by Ambrosio, Gigli, and Savary coincide with the definition I am giving here. So we know what is a Sobolev function on RD. We know what is a Sobolev function on the real line. And you can define the analog of a Sobolev function on a metric space. And this is what I want to, you call it ACP function, 0, 1, to a metric space. Yes. Let SD be a metric space. And let P be in 1 plus infinity. We say that sigma from 0, 1 into S is a P absolutely continuous. And we write sigma is in ACP 0, 1 S if there exists beta in LP of AB such that the distance between sigma T1, sigma T2 is less than the interval from T1 to T2, beta of tau, d tau, for every 0 less than T1, less than T2, less than 1. And it is well known that W1P of the real line is completely characterized by this relation. Now, here is a remarkable theorem by Ambrosio, Gigli, and Savary. Let sigma be from 0, 1 to the set of probability measure of finite second moment. The following are equivalent. Sigma is in AC2 of 0, 1, P2 of RD. There exists a vector field from 0, 1 cross RD into RD, Borel, such that in the sense of distribution, the derivative of sigma with respect to time plus the divergence of sigma v equal to 0 in the sense of distribution on 0, 1 cross RD. And the kinetic energy, the integral from 0 to 1 dt, the integral over RD of v of tx square sigma t dx is finite. So my notation sigma t means sigma of t. So let us compare this to what I wrote earlier. This theorem of Ambrosio, Gigli, and Savary is saying if you have some regularity of sigma, you can associate to it a vector field. And this vector field V will play the role of the tangent vector to the path sigma at time t. And above here, I am saying that the tangent vector to a map S0 will be a vector field. And there is a relation between the vector field appearing there and the vector field appearing here. The relation is through that. So if you look at this gradient, it is a function defined on omega. That gradient is a function defined on RD. But if you compose it with x0, then you get a composition which is defined on omega. And the V appearing here will be related to the tangent vector appearing there by that relation. So, theorem. Suppose U is defined from a set of probability measure D into R is of class C1. So the gradient exists and is continuous, which means that I leave the function to obtain a function U bar. I know what it means that the gradient of U bar exists. And on a Hilbert space, I know how to define the continuity of the gradient of U bar. Let sigma V be as in the previous theorem. Then there exists a vector field for almost every t in 0, 1. There exists a vector field psi t, depend on t, from RD to RD, such that if you differentiate with respect to time u of sigma t, and you compute the derivative at time t, what you get is the integral over RD psi t of x Vt of x sigma t dx. Furthermore, psi t is uniquely determined if we impose that psi t is in the set of gradient function on Rd. So if we impose that psi t is a gradient of a function of class C infinity of compact support, it is uniquely determined. However, if you impose that condition, you will rarely find psi t satisfying this condition. So if you want that condition, an analog of the condition which will be always satisfied is you are going to close this with respect to the norm. If I don't close it, I have a space which is not a Banach space, which is not a Hilbert space. If I close it, I have a Hilbert space. And I am saying not only it is uniquely determined, but it exists. We call psi t the gradient of u at sigma t. And we write the gradient of u at sigma t is psi t. So what I did, you can do something similar for the subdifferential and the differential. Now, since we have this, we are well equipped to write what the master equation is. I am not going to write the whole thing, but find u from 0 t cross td cross the set of probability measure on td into R, such that something happened. This thing which is going to happen will involve the gradient with respect to q of u at t q mu. We know well how to compute a gradient in RD. It will involve the gradient with respect to mu of u t q at mu. This is a vector. That is a map from RD. According to that definition, this is a map which is in L2 of the torus to RD, where the L2 is taken with respect to the measure mu. And furthermore, I am going to impose that it belongs to a smaller set than that. It belongs to a set which has a spatial structure. It belongs to this gradient can be approximated by gradient of function of class C infinity and compact support. Therefore, the non-local expression I am going to write will be the integral over Td, gradient mu of u t q mu at z, because this is a map which I can apply to z, gradient q u of t dz mu dz plus something. So my non-local term, which I am going to write next time, include an expression like this. So I am going to stop here.